Go to current slide. Okay. And go over a few announcements. The first, I think I asked this, well, maybe, I can't remember if I asked you before or not. Are you in a mini-term course? PE?
Yeah, I mean,
Right, okay, yeah. Yeah, those just were open last week, so don't feel like the Lone Ranger. And also, if you know of anyone else, I know Donna knows it from this morning. I don't know if he's done his or not. But anyway, those are, I think, is Thomas in the same one?
Yeah.
Okay. Yeah, he knows what I can remember him. That's it. But anyway, those of you, they didn't say when they would close. They usually give you a week or two after. So just try to get those done as soon as possible. All right, now that leads to something else. And that means since the first mini-term is coming to an end Wednesday, okay, I mean second mini-term starts Thursday, and that means we're midterm is midnight Wednesday night or Thursday morning, whatever you want to say. And sometime shortly after that, they usually ask for us to submit midterm progress reports, which means we report on students who have a D or an F at midterm. And in this class, I have 0 research papers and 1 first test in already. And that's all, folks. That's it. So I need some sort of score by, oh, you got one?
well, I was going to ask you something.
That's all right. Yeah,
I know
you can ask.
You can't answer the question.
Right.
But I kind of need help
Right.
pointed in the right
Right.
direction.
Okay. And have that as your first question or a question when we get to this. Okay. All right. So anyway, I do need to have some score in, I would say sometime next week. Okay. By Wednesday of next week, which for this class is sometime next week. Okay, so that's what I was wanting to encourage, because I don't want to put them, any of you folks who are really sharp students is failing or to get F midterm, which doesn't really make any difference anyway, but you don't need the hassle. I don't need to have to write it down. Okay, so there's that. Now, that's sort of school-wide stuff. Here's a little bit more of my personal schedule. This week is a mess, okay? In the sense of, I've got a doctor's appointment tomorrow morning. My hematologist only sees patients on Tuesday mornings. So I couldn't schedule any other time. So I have a doctor's appointment tomorrow. It's at the appointment's at 10:40, but I have to be there for lab work at 9:40. And that enabled Josh to get here. Okay, the bottom part of the alphabet, even though you're in the top half of the alphabet, are here strongly. The upper part is missing completely. Okay, so I have a doctor's appointment where I was just explaining. It really doesn't affect this class much. It does possibly affect your linear algebra class a little bit. But I told you this Thursday, didn't I? Or you may have been, yeah, you may have come in late. So let me go over this. My doctor's appointment's at 10:40, okay? But I have to be there for blood work at 9:40. So I have to leave campus at 9 o'clock. So that means I come to campus at 8, have office hours till 8:30, meet a class for 30 minutes, and then turn around and leave and go back to Kirkland Clinic. But that's what I'm doing. Hopefully, what's that?
Thursday?
That's tomorrow, Tuesday.
Okay.
Tuesday. Okay. So Tuesday, that's happening. I'm hoping the appointment will be over with by 11. No guarantee of that, but I'm hoping. Usually it's not that quick, but I'm hoping. So that means I should be back on campus by 11:45. Now our class starts at 11:30. Okay. So therefore, the odds are I will be late to class tomorrow, okay? But I will be here at some point. I don't know what point that will be, but I'll be here. As soon as I get here, I'll come in and teach the class. Okay. So that's tomorrow. Wednesday, normal day. Thursday, I'm out all day long. Almost, not quite. I have a meeting in Tuscaloosa that starts something like 8:10 or something like that. So that means I will be well past the school by 8 o'clock. So I will not be on campus in the morning, 8 to 10, on Thursday morning, 8 to 10, 8 to 8:30 on Thursday morning. I'll miss completely my 8:30 class. They're having a test. Dr. Thomas is going to proctor that. I'll miss completely my 10 o'clock class. They're just going to have to catch it up on YouTube videos. My 11:30 class, which is your class, not be here at all, so that one you'll pick up on YouTube videos. And then my 1:15 class, first day of a second mini-term class, I have my work-study student here giving I'm calling it a lab quiz. They have to go over things in Blackboard and other things to answer quiz questions to cover my first day of class. I will be back on campus sometime. The meeting, I think, is over about 3:30 or so, and it's in Tuscaloosa, so I should be back here by 4:30. I don't know how long it takes to get from the Fire College at Shelton State back here, but whenever I can get back here, I'll be here until 6 o'clock. So I will be on campus, but it'll be late, but I will be here on campus because I have to turn in attendance for that first mini-term class. Okay, Friday, I think, is going to be a normal day. It seems like everything's stacking up for that Friday, but I do have a doctor's appointment in the afternoon, but I think it's late enough in the afternoon I won't have to leave early. But if I do, it won't be very much time, 15, 30 minutes, something like that. So anyway, it's a crazy week this week. All right. Now, one other thing. Wish more people were here. What is tomorrow? Second? March the 3rd. What's special tomorrow? Come on.
Oh, second MTH Section?
No. It's primary day. Y'all, please tell me you know what I'm talking about. Alabama votes for the primary. Republican and Democratic primary votes are tomorrow, 7 to 7. And please tell me you're voting. Please do not ever miss an opportunity to vote. Not only is it a right, it's a responsibility. I mean, it's please get into the habit voting every time the polls are open. And I'm really serious about this. With such low turnout as we typically have in Alabama, and then, I mean, oftentimes it's less than 50%. So that means the winner of an election can have a quarter of the registered voters voting for him or her. That's not a democracy, okay? That's a small handful of people controlling everything. Please, folks, vote. So tonight, homework exercise, go home, find out about the candidates, decide who you're going to vote for, and vote tomorrow. Work it, plan it into your schedule. I have, like you said, a crazy day tomorrow. I have to be here. I'm going to try to get here as soon before 8 as possible, be running back and forth, but I'm going to leave this campus by 6, or shortly after 6, so I can be back at the polling station by before 7 o'clock, so I'm guaranteed to be able to vote. Please make it a priority for all of your life. Please do it. Okay. That's my paid political announcement. Okay. Any questions on anything so far? All right. Yeah.
Yeah, this is one test.
Just tell me which one I got it.
It's number 5.
5.
I guess I need help finding an example in the book.
Okay. All right. I've had another question about that. I don't remember if it was on. Yeah, let me see what I can find. Here we go. Okay. Dawson's here. Still the bottom part of the alphabet doing quite well. Top part not doing as well. Okay. All right. Here we have an X, Y, and Z. The question, and Dawson's already answered this one correctly, by the way, is determine whether the lines given below intersect, and if so, find the point of intersection between them. Okay? I think I'll go on and use these numbers. I won't tell you. I'll try to stop short of telling you an answer. I know you don't want to do that. Here's the first. X is equal to -7 plus 5t. I can't write. Okay. Y is equal to 8 plus 7t. And Z is equal to -12 plus 7t. Wait, let me write my Z in there. This is ugly. Okay. -12 plus 7t. If I'm writing anything down wrong, correct me.
We can't see it.
What's that?
We can't see it. Projecting.
Well, so what? You should be able to visualize what I'm saying. I mean, obviously. Okay. Yeah, it's coming on now. Plus 70. It's going to take me that long to get these written. Goodness, my nose is itching. Okay. X is equal, that's one line in 3 space. Second line, X is equal to 7 plus 3X. Y is equal to 24 plus 3S. And Z is equal to 4 plus 3S. Is that right? Looks right to me. Okay. Now, I don't usually like doing this, but I think in this case it might be instructive. Okay. Especially this second line here. And the reason I picked that out is that each of the parameters is somewhat similar. The plus 3s is on the end of each one. So let's say we have 7, we're going 7 in that direction, plus 3 times some parameter s, okay? 4, or 24, whoa, way out there, plus same parameter 3s, and z is 4 plus some parameter 3s, okay? Now, I hope you realize already a point that's common to all, that's on these lines are 7, 24, and 4. Okay, 7, 24, and 4, so that would be something somewhere about like here. 4 up, 24 this way, 7 that way. Okay, some point out here. And then from there, 3s, I mean, you go from that point, and s is equal to 1, 3 more in each direction, 3 more in each direction. So it's heading off somewhere that way, right? Okay. Just to give you sort of a visualization of what's going on here. Okay. This next point, line here, starts at -7, somewhere way back there somewhere, +8, and -12, somewhere down there. And the y and z are going in a similar fashion, 7t, but the x is going at a rate of 5t. Now, it says determine whether the lines intersect, and that's the first question, and if so, at what point? Okay. Now, if this were in 2 space, we didn't have z's here, would you be able to answer that question?
Well, it would just be x and y, just 2 lines.
What's that?
It would just be x and y, just 2 lines.
Yeah, you have x's and y's, and let's just do those.
-7 is 5.
-7, 8. Okay, it would start right here, the first one, and the second one is 7, 24. Ooh. 24 is actually off scale here. Okay. But then this one here is going 5s to 7, 5t to 7t. Okay, so it's increasing your x is increasing at a rate of 5 per unit t, and y is going 7 per unit t. So in other words, the ratio of y to x, which would be kind of slopish, would be 7t to 5t, right? Or 7/5 t, okay? In a sense. Whereas this one would be a 1-to-1. So, in a sense, those have different slopes. They've got to intersect. Okay. Now, you don't quite have that same kind of thing in 3 space, because this line could have one slope here, and the slope could be here, or a totally different slope, but they would never intersect because they're in 3 dimensions. Okay, so you have a little bit more to worry about there. So this is all background, okay? So um, um, I'm pretty sure, I want to point you in the right direction here. Make sure I get in the right section. Okay, I'm sorry. Um, okay. Probably the simplest answer to the first, if you think back to 11.5 on page 793. Well, wait, that's not quite right. No, sorry. Okay. 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 One thing you can do right off the bat is tell whether they're perpendicular lines or not. And I think you can almost tell, parallel lines or not. And I think you can tell they're not, but there are ways to determine that, and that's by their what? Try not to give too much away here. Yeah, okay. Right. And how do you determine that?
Well, it's like the
Okay.
you take the angle parenthesis.
The what now?
Like it's like the angle parenthesis thing.
The angle parentheses?
Yeah. What's that called? Component notation.
Okay.
Component one.
Okay.
Of the X, Y, and Z.
Let's see. Remember what we call the direction numbers? What were they? Do you remember? Yeah. A, B, C. Okay. And this is A, B, C. Now, if they were parallel, they would have, okay, if the direction numbers A, B, and C are all non-zero, then you can eliminate, okay, I'm sorry, you can write these, well, parallel symmetric equations. Now, if you did that for each one of those, okay, each one of the lines. Let's see if I'm right on this. What we want to know is if there's X, Y, and Z that are in common with those. So if I say the symmetric equations, would you know what I was talking about there? Page 787. See the symmetric equations there?
So basically, the symmetric equations, you take the parametric equations and solve for T.
If you solve each of those for T and each of these for S, you get the symmetric equations, right? Okay. Now, so you can visualize what the symmetric equation would be. Maybe not know exactly what it is, but you know what it is. And that needs to be equal, the X for this one has to be equal for the X for that. Okay? Maybe you could do it even without the symmetric equation. Let me just take a look and see. But I believe that will get you going in the right direction, won't it? You've eliminated the T and the S then, and let me make sure what I'm saying is but I mean, even with those equations, let's see. I don't think you even need that. Let's see. If you try to solve these simultaneously, you get you want the x's to be the same, right? With a point in common. Okay? So this is equal to that, right? And you get one equation in S and T, right? And then you do the same thing with this one, okay? And you get a second equation with S and T. It's got to be true. And then you can solve those two equations simultaneously and get what, you know, S and T are. Now, if you come up with something like, if you try to do that with these two, since these are the same here, I don't think it'll get you anywhere, okay? But these two, I think, will get you a value for S and T, plug them in, and that should give you the points. Dawson, is that the way you did it? Or, I know we talked about it, yeah. Yeah, so you don't even need the symmetric equations, I think.
So
that would work better. You know, this x has to be equal to that x, so have this equal to that. This y has to be equal to that y, so have this equal to that. That gives you two equations in S and T, solve them simultaneously. Does that make sense? Yeah. Okay. I know you had a question too, but I don't remember if this is how I answered it for you. I think we worked it out that way, didn't we? I can't remember the approach we took. I think we took a slightly different approach, but this will get you the same way, won't it?
Yeah, that's what we did.
It is, okay. I couldn't remember. I was thinking we did something a little differently, and I was trying to point them in that same direction. I said, well, why do that? Let's just set those two equal to each other. And the reason I didn't do y and z is I think they come up a trivial solution, kind of, because you have the same coefficients for S and T, so I think you'll come up with a trivial answer there, but these two will not be necessarily a trivial answer. And then check it and see. Is that good enough? Okay. All right. Any other questions? Good questions. Okay. That was a different question from any that I could remember seeing in the book. Okay. But I believe that's the section you would go to. I was trying to think if there was a way that the book had done anything similar, and I just couldn't see anything that they had. Maybe I'm missing it. Oh, actually, I'm sorry. 11.5 exercises, 33 and 35 are both like that. And these exercises determine whether the lines intersect. If so, find the point of intersection. And they also asked for the angle between the lines. Our question did not. So, if nothing else, go to calchat.com for tutorial help, and that'll give you maybe a different way to do it, but this way will work.
Okay.
Yeah.
Thank you.
All right. Now, good question, by the way.
And I have one more question.
Okay.
On test. It's number 9.
9. Hold on.
For this one, I've used the book to look for, like on number 7, I found the one in the book, quadrant surface that had all positives.
Right.
To figure out what shape it was. But
Right.
number 9 has 1 positive x and 2 negatives for y and z.
Right.
And that doesn't match any of them.
Well, and notice that's equal to a 1 there, right?
Right.
Okay. Wait a minute. Where were you looking in the book?
Page 800.
800, exactly. Okay. And what's the third one, 800?
The hyperbola with the 2 sheets, that's the one I guess.
Huh?
I guess that one.
Well, it has 1 positive, 2 negatives equal 1, right?
So it works. It doesn't matter what the unknown is. The x.
Oh, yeah, okay. What that does, okay, now I see your question. If z is the single positive, I mean, they're all three unknown, but if z is a single positive, that means that's your axis.
Okay.
If on this one, x is your single positive, so that's your axis.
That's what I thought. I just wasn't sure
Yeah.
because this was the x and that was.
Yeah, they showed them all as z's being the major axis, but in some of the exercises, like example 2, y was your axis, and that was a hyperboloid of 2 sheets. Right? And example 3 was a paraboloid, and that was a elliptic paraboloid, and there your y was your axis. And yeah. Okay.
Thanks.
All right, glad to. All right, now, and all that doing around, I lost my page, but I can get it back pretty easily here. Okay. My memory is we were starting at 12.4. Is that where you had it? Okay, we haven't done anything in 12.4 yet, right? Okay, chapter 12 is still any other questions before we move on? Chapter 12 is vector value functions, and 12.4 is tangent vectors and normal vectors. Okay? Our objectives here are to find a unit tangent vector and a principal unit normal vector at a point on a space curve. Space curve, somewhere out here, a unit tangent vector and a principal unit normal vector. Now, when you see the word principal pop up in a place that's sort of unexpected, that usually means there's two directions to it. You want the positive, okay? That's usually what principal means, okay? And indeed, that would be the case. If this is your vector that happens to be a unit tangent vector here, some curve doing like this, then its normal vector could be going that way or this way. The principal is the one that's outside the curvature. Well, we'll get to that. Okay. That's what we mean by principal unit normal vector at a point on a space curve. We'll also find the tangential and normal components of an acceleration. That's doing your application for position, velocities, and acceleration. So let's start with tangent vectors and normal vectors. The velocity vector points in the direction of motion. Okay? If an object is going on a curve like this, the tangent vector, velocity vector is pointing on the direction tangent to the curve in the direction the object is moving. Okay? This observation leads to this next definition, which applies to any smooth curve, not just for which the parameter represents time. Okay? We use t a lot. A lot of times it does mean time, but it doesn't have to. So here's the definition of a unit tangent vector. If C is any smooth curve, okay, could be out there in space or in a plane, represented by R, bold R is a vector, on an open interval I. Now, I will be the interval of your parameter t, or s, or whatever your parameter happens to be. Okay? The unit tangent vector, unfortunately they use t's a lot. Capital T bolded means unit tangent vector. Okay? Little t is your parameter t. Those have absolutely nothing to do with each other. They just happen to be the same letter. One's capital and one lowercase. This is a unit tangent vector. And here's how we define it. Goodness, my nose is itching. We must be going to have time. Okay. If your velocity vector is in the direction of motion, that's your r prime of t, right? Tangent to the curve. It's tangent to the curve there. So it has to be in the direction of r prime of t. Well, then just make it a unit vector. So divide by the magnitude of r prime of t. That gives you a vector in the direction of motion, and it makes it a unit vector by dividing by its magnitude. Now, of course, this indicates that r prime of t, your first derivative of your displacement vector cannot be zero. If it were, all bets are off because you're trying to divide by zero, because the magnitude of the zero vector is zero. We know that a curve is smooth on an interval when r prime of t is continuous and non-zero on that interval. When r prime is continuous and not zero on the interval. So smoothness is sufficient to guarantee that a curve has a unit tangent vector. Okay? Now, so we're going to do it. Find the unit tangent vector to the curve given by, and this is a plane curve, two-dimensional curve, r of t is equal to ti plus t2j when t is equal to 1. Okay? So how are we going to do that? We want the unit tangent vector. That's capital T. Now, since I can't bold, normally for a vector I'll put an arrow over it. But if it's a unit vector, I like to put a hat on it to indicate it's a unit vector. And that's what we're looking for, the unit tangent vector as a function of this parameter, little t. Now, they both are t's, but they have nothing to do with each other. Okay? Except one depends on the other. What would be our approach?
Well, first we need to take the derivative.
Absolutely. R prime of t. And that is a vector, meaning an arrow, but not necessarily a unit vector. And what would that be?
So it would be
I plus 2tj. Okay? Done the first step perfectly well.
Now we take the magnitude.
Magnitude of that. See, magnitude of r prime of t. And what would that be?
Square root of 1 plus 2t squared, so it's 1 plus square root of 1 plus 4t squared.
Perfect. Okay? And what you do with that?
Divide r prime t by
Yeah. Okay? Except right now, we happen to know at what value, and that's good for any vector in that direction, any velocity vector, whatever vector it happens to be, position vector, velocity vector, whatever, at any time t. But we happen to know what, and it doesn't have to be time even, any value t. We happen to know where we want it. And where is that? At 1. I say 1 and cross it, okay? Duh, okay. And what would that be? I plus 2j over square root of 5, which you may want to write, I think probably the book does, 1 over root 5 t. I mean, goodness gracious, keep wanting to get a t in there somewhere. I plus 2 over root 5 j. Okay, you buy that? Yay or nay? Okay, now, a very easy, simple, and almost redundant test to make sure that's a unit vector is to do what? Square that. That gives you 1 over 5 plus, which is? Yes, that makes it a unit vector, doesn't it? The square root of 1 is 1. So that's a real good check to see if you've done it right. And you did. Very good. Of all the ways they chose to write it, they chose to write it this way. 1 over root 5 times I plus 2j. Which is fine. Another perfectly good way to write it. I kind of prefer to write it in guess what? Component notation. That's how I almost always default to write my vectors. Okay? So, let's see the steps they took. I think they're going to be very similar, if not exactly what you did. Derivative, take that first as I plus 2tj. Unit tangent vector would be the derivative over the magnitude of derivative, which would be, and they put the 1 over 1 plus square root of 4, the square root of 1 plus 4t squared times I plus 2tj. And when t is equal to 1, that would be 1 over root 5 times I plus 2tj. Okay. Now, in order to do their graphic the way they did, what you have to also do is plug in the 1 here and find your initial value. And what would your initial value be? What is your R of 1? Yeah. I plus j. And that's why they started at the point 1, 1. 1i plus 1j. So you start here, that is the unit tangent vector at that point, okay? And this has a slope, it's hard to say what the slope is, but 1 over root 5 in the I direction, that's going to be, root 5 is something greater than 2, right? So your x is increasing at a 1, less than 1/2 per time, and this is going up at 2, just a little less than 1. So your x is increasing slowly, your y is increasing a little bit faster. Well, your x component here is that thing that's less than 1/2, and your y component here is something that's a little bit less than 1. And sure enough, they've drawn it pretty well. Less than 1/2 here and less than 1 here. So the tip of their arrow is just about where that vector is. Okay. Does that make sense? Okay. You measure the vector from that point, that initial point. Okay. All right. The tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector. Of course, the tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector at that point. Okay? In example 2, the unit tangent vector is used to find the tangent line at a point on a helix. So this is going to be a 3-dimensional shape. Here's example 2. Find the unit tangent vector and then find a set of parametric equations for the tangent line to the helix given by this position vector. R of t is equal to 2 cosine I, 2 cosine ti, plus 2 sine tj, plus tk. Now at the point, root 2 pi fourths. Okay? Let's make sure that makes internal sense. Okay? Let's start with the pi fourths being your t, right? From the k value here, right? And what's the cosine of pi fourths? 2 root 2. Say again? 2 over 2. Root 2 over 2. I couldn't get the root. Okay. Root 2 over 2. Multiply that by 2. You just get root 2. And sine of that is also root 2 over 2. Multiplied by 2. Yeah. So yeah, this is internally consistent. Okay. Okay, if t is equal to pi 4, that's your xy value. So that is on that curve. Okay, so how are you going to find the unit tangent vector? Very similar to what we did last time. Yeah, r prime of t is equal to sine ti plus cosine tj plus k. Perfect. And what do you do with that? Magnitude of that r prime of t is equal to what? For sine squared t plus 4 cosine squared t plus what? 1. Okay, good. Okay. Now, let's group those first two terms together. What do they give you? I'm sorry?
Factor out the 4, and then it just gives you 1.
Okay, so that'd be 4 times 1 plus 1, and that would give you, they like root 5, don't they? Okay, all right, we've run into that again. Okay, that is the magnitude of your velocity vector, you might say. Okay? Your first derivative vector, let's leave it like that. Okay? How do you use that to find your unit tangent vector? Okay, and what does that give you? Where did I get a square from? I do not know. Okay, duh. It's been a strange day today, okay? And I can't write. Goodness gracious. Okay. I think I got it right that time. Okay. Do you agree? It would be r prime over the magnitude of r prime. And that would be minus 2 over root 5 times sine t I plus 2 over root 5 times cosine t j plus 1 over root 5 times k. Yay or no? All right. So there's the first part. Find t of t, done it. Okay? Then find a set of parametric equations for the tangent line to the helix, given by that, at the point root 2, 4. Okay? Now, let's go back one slide. The tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector. Okay? We just found the unit tangent vector. Okay? All right. So, what are we going to need to do here then? Well, one thing you might want to do, since you're looking for a set of parametric equations for the tangent line to the helix, this helix, at this point, let's go on and figure out what the unit tangent vector is at that point. And what would that be? Unit tangent vector at the point that. Okay? Well, again, easiest to start here. The t has to be pi fourths, right? Because it's tk, and the t here is, the k component here is pi fourths. So t is equal to pi fourths. So t of, say, pi fourths and write 5 fourths, okay? There is something seriously wrong with my head today. Okay, pi fourths. And that would be what? Okay. Say it again. 1 over root 5. Is that what you said? Okay. All right. Now, I really don't particularly like writing them that way. I think I would be just as tempted to do the square root of 2/5 I minus square root of 2/5 I plus the square root of 2/5 j plus 1 over, you could say the square root of 1 over 1 of 1/5 k. Now, that's no better. It's just a little easier to write. Well, I like to write that many radicals. But can we check this quickly and see if that is indeed a unit tangent vector? What's this squared? Negative 2 over 5. When you square a negative, you get positive. So that's 2/5. 2/5. That's 4/5. 2/5 plus 2/5 is 4/5 plus. That square root is 3/5. Okay. 2/5 plus 2/5 plus 4/5 is 1/5. Right. And that would be 4/5 plus 1/5 is 5/5. So you got 1 again. So always a nice little check to do to make sure what you're doing, you're starting on the right foot. Okay, so I think we found T of t in general. We also found T of pi fourths in specific. Okay, so this is your unit tangent vector at pi fourths. Okay, now, so we got that. Find the set of parametric equations for the tangent line to the helix given by this expression down here. At this point here, we found the tangent line at that point, the unit tangent line at that point. What is going to give us the parametric equations? What would your x be? We were just doing those. Wasn't it something like an x1, x1 plus at? Now, let's see, I don't want to mess up my t's here. That would be what your parametric equation looks like. Now, I'm worried a little bit about using t here because we've used t over here too. So let's call this one S then. Not that it really matters that much because they're, okay. So what is that parametric equation going to look like? What is your A in this problem? Second? 2? 2/5? Is that what you meant? Huh? Or how about square root of 2/5? Okay. Only it would be minus square root of 2/5, wouldn't it? Okay. In other words, your
root 2 plus.
it can be any multiple of it. And since they're all going to have a root 5 on the bottom, yeah, you can just leave it. But it needs to be a minus root 2 because of that minus sign there. Your direction numbers are basically these numbers here or some multiple of those numbers. Constant multiple, okay? So just to make it a little easier, let's multiply everything or divide out the 1 over root 5. And so the the A is going to be negative root 2. I'm going to write the parameter S. I think the book, yeah, it uses S too. Good for them. Okay, but what's going to be your X sub 1? That's your root 2. Okay. So that's this root 2, not this root 2, okay? So your X is equal to that. Tell me what the Y would be. Root 2 plus root 2 S, and your Z, pi over 4 plus S. Perfect. Those are perfectly fine things. You could have it over root 5s if you wanted to. You could have it over 17s if you wanted to do over 17s. It doesn't matter. Just anything like that will work. And they went to S's too, so you wouldn't confuse them with the T's that we had earlier. Okay. Now, that would be, those are the parametric equations of this particular tangent line at that point. And of course, when S is equal to 0, you're at that point there. When S is equal to 0, you're at root 2 root t pi fourths. Yeah. And that's where you needed to be. And then for positive S's, you're go to the right, upward and to the right on that, and negative S's would be downward and to the left, so to speak, of that. Okay. Now, let's go on and see how they do it. So you can actually, I was talking about how it looked. Let's see how it looks. Okay, derivative of R of t is have they left off a minus sign? No, they wrote, okay, I'm sorry. I was looking, I thought that this was the derivative. This is the derivative of minus 2 sine ti plus 2 cosine tj plus k, which implies that the magnitude of that r prime of t is 4 sine squared plus 4 cosine squared plus 1. Okay? Which, when t is equal to what? No. I don't like, well, no. Okay. It doesn't matter. At any value t, this is root 5, isn't it? Because sine squared t plus cosine t squared t is always equal to 1. So the magnitude of your velocity vector, your speed, is always going to be root 5. You're moving along a helix at a constant speed, not a constant velocity because it's always changing direction, but at a constant speed of root 5. Okay? Therefore, the unit tangent vector is that r prime that we calculated here divided by root 5, which is 1 over root 5 times times 2 negative 2 sine ti plus 2 cosine tj plus k. I was saying, where's our root 2? That's when we plug in t equal. So at the point, root 2, pi fourths, t is equal to pi fourths because of that characteristic, it was a tk, so the t had to be pi fourths. So the unit tangent vector here will be at t is equal to pi fourths, would be 1 over root 5 from there, minus 2 times root 2 over 2i plus 2 times root 2 over 2j plus k, and the 2's divide out, you get minus 2i plus 2j plus k. Okay. Now, using the direction numbers, minus root 2, and 1, and again, it's the coefficients here, okay? Now, if you didn't like using radicals, you could have multiplied every one of those by a root 2, and that would have given you minus 2i plus 2j plus root 2k. You still have a radical in it, so why do it? You know, I can't think of any way you get rid of the radicals because it's going to be in one of those two terms anyway. If you wanted it over the root 5s, you could have had it over the root 5s. That doesn't matter either. Any multiple of those, okay? And those are your direction numbers, okay? A is negative root 2, B is root 2, and C is 1. And the point is, point of tangency, root 2, pi fourths. Now, the problem with this is you got so many root 2's in there, keep up with which one's that. The x of I is this root 2, the a is that minus root 2, okay? Your y is root 2 minus root 2s. Again, they used s here to keep it from confusing from the t's from before. Your y is going to be this root 2 plus that root 2s. y1 plus bs, which is root 2 plus that root 2s. And then your z is going to be your z1, which is pi fourths, plus, and your c here is 1. S, pi fourths plus s. Okay? So there are your parametric equations at that point. And that's all they asked for. But in addition to that, they draw the curve for you. Here's the helix, starting here at 2, 0, 0. Okay? T is equal to 0. This will be 2, 0, 0. And then it moves along, and here it's going to be at root 2, pi fourths. And then it moves all along here, and here it's curving back around here and picking up and paralleling with this. It just keeps going up like that. Now, the tangent line here is determined by the unit tangent vector at that point, which is what we got from r prime over r, and then r prime over magnitude of r prime. And then the direction values are any multiple of those coefficients. They just use the root 2 minus root 2 root 2 and 1. Now, and before I say this, I want to make sure that I'm right about it. It's been bugging me all along. I just didn't want to say it because I didn't want to make it too confusing. That's not what I want. Here's what I want. Let me make sure. Okay. I don't want to say it until I'm sure of it. We if you left this off, that's what you have left is your R prime, right? No, not quite. Nope, I went in the wrong direction. Yeah, no, it is. It is. Leave that off, and that's your R prime. Plug in t equal 1. No, t equals pi fourths, just like we did. And this becomes minus root 2i plus root 2j plus 1k. That's what we use. So why in the world do we have to use the unit tangent vector? Any tangent would have worked. The velocity vector would have worked. It was simpler in that you didn't have the square root. And we didn't use the square root, you know. When we turned around and got our direction vectors, we just ignored this and used those. And that's exactly what you got if you plugged in pi fourths there, there, there. Okay? Well, you don't have anything to plug in there, here and here. That's exactly what you would have gotten. So I've been sort of scratching my head wondering, why did they make a special point of using the unit tangent vector? The tangent vector would have worked fine. You know, your first derivative of your displacement vector. And that's exactly what they used here. They used the only the numerator part, which was exactly that, minus root 2, 1. And I couldn't figure out why they did it otherwise, but they did. But that's okay. All right. In example 2, that's what they're getting at here. There are infinitely many vectors that are, okay, I'm sorry. No, this is not what they're getting at here. Infinitely many vectors that are orthogonal to the tangent vector, the unit tangent vector t of t. One of these is the vector t prime of t. Okay? Now, this follows from a property that says t dot t is t prime squared, the magnitude of t squared. And that's 1 because the magnitude of the unit tangent vector is 1, and you square 1 and you get 1. Now, that implies that the unit tangent vector dot product with the first derivative of the unit tangent vector is 0. Now, where did they jump the rabbit to get that? Well, it's back in a table of properties of the dot product. And I don't know if you recall those or not. I meant to look it up beforehand, but I didn't. Let me go back to the dot product, which is 11.3 maybe. Yeah. Maybe not. Well, I thought it was there. Well, maybe it's coming up. That's what I'm getting it confused by. I don't see it in here handy now, but that's okay. Oh, yeah. It sort of is, but now, remember that if you take the derivative of this, it's just like the product rule before, that this times the derivative of that plus this times the derivative of that, which gives you exactly the same thing. And that's taking the derivative of this side, and the derivative of this side is 0. Well, this would be 2 times t of t dot t prime of t. That has to be 0. So it's pretty easy to derive from there too. Now, by normalizing this vector here, just because you're taking the derivative of a unit vector doesn't guarantee you're going to have a unit vector. Okay? So then you have to normalize that again, which means divide by its magnitude. Okay? You obtain a special vector called the principal unit normal vector. Okay? So here's the definition of the principal unit normal vector. Let C be some smooth curve represented by R, tracing that curve out, on an open interval I. That open interval is I of t, since we're using that as our parameter here. If t prime of t is not the 0 vector, okay? Now, if the t prime of t is not the 0 vector, then the principal unit normal vector is defined as principal unit normal vector is your derivative of your unit tangent vector, which is not necessarily a unit vector anymore, divided by the magnitude of the derivative of your unit normal vector. Now here I have problems writing these things, because usually I like to put, since t is a unit vector, I usually like to put a hat on it, But I don't like to put a hat on it here because T prime is not necessarily a unit vector, so I don't want you to think that has to be a unit vector. So there, I'll go back to putting arrows over those derivatives. If I was writing unit tangent vector, I would put the caret over it, but the derivative of that unit vector is going to have an arrow over it because arrows are still good. I mean, there's nothing wrong with it. All right, so we're ready for example 3. Find n of t and n of 1 for the curve represented by r of t is equal to 3ti plus 2t squared j. Where would you begin? Take a derivative, always a good answer, okay? And what would that be? Three I plus 4tj. Perfect. Okay? Then what do you do? Magnitude of that. Magnitude of r prime. Oops. Yuck, that's ugly. Yuck, that's uglier. Okay. And what would that be? Help me, somebody. 9 plus. Yep. Okay. Now what do you do? Help me, somebody.
You put the derivative over the
Okay, and that will give you unit tangent vector as a function of time, and that would be, I think I'm going to cheat like they do and put this on the outside, 1 over the square root of 9 plus 16t squared times 3i plus 4tj. Now I'm going to regret that I did that, okay? Because what's the next thing we've got to do? I am regretting it already, so I'm going to go back and change this. Okay. I think that's better. Now what? Yeah, got to take the derivative of that. Now I'm going to change that caret to an arrow. Not that the unit tangent vector is no longer the unit tangent vector, but it's a derivative. It's not necessarily a unit vector, so I'm going to go back this way. And what will that be? Oh, my word. Let me write this another way. I'll write it down here. 3 times 9 plus 16t squared to the, what power? Negative 1/2 power. Okay, I plus 4t times 9 plus 16t squared to the negative 1/2 power j. I'm running out of room rapidly. Okay, that's just a tad easier to take its derivative. And what would that be? All right. right? I went back and put it over the 96T halves, which then this would be 38T, I think. Something's not right there, is it?
-48.
Yeah, wait. There's something dreadfully wrong there. Let me go back and start over. Okay. That's the 32T. Wait.
Should be a 48.
Yeah. 32T times yeah, 48T minus 48T.
And then that's out to the,
Okay, that's the I, right?
that's the -3 halves.
All right, where are you now? You on the J?
I just did the exponent. The -3 halves.
-3 halves. Okay, got it.
Plus,
Okay. I'm going to write it down a minus because I think it's going to turn out being a minus. But now this is a mess, isn't it? That's what you got to do.
that would be -2.
Product rule, right? Oh, yeah. All right. That's good stuff, man. What does that give you? Well, so hold off a minute. Not necessarily. I'm going to put the plus back in there, okay, because I don't know which one you're going to do first. I knew which one I was going to do first, but I didn't know which one you're going to do first. So which are you going to do first?
So it's,
I'm sorry?
so if I was D1 times so the plus 4T
Okay.
times
4T times
32T
32T times still got that -1/2, don't you? 9 plus 16T squared to the -3 halves, right? Yay or nay? Okay. Plus the second part,
4
all that times J. Okay. Now, guess what we got to do next? The magnitude of that. I'd just as soon not to, okay? And what they do, and it kind of cheats a little bit, but what they do here is when they get to this point, I'm beginning to think I've lost. Remember how I started off and I said I was going to do this and I changed my mind? I wish I hadn't changed my mind. Because they kept it in that form And I mean, it's an awful mess, okay? I'm trying to okay. In the first place, if you do 2 into that would be 2, that would be no, okay. Okay, what they did is factor out, like I was starting to begin with, the 1 over square root of 9 plus 16t squared, okay? And when they go to differentiate that with respect to t, they say they're using theorem 12.2, which is way back, way back, way back, way back, way back, goodness gracious, 12.1, 12.2, okay? I don't see where they're really doing it, except they're doing basically it's number 6 back there on properties of derivatives. I believe that's the one they're talking about, where they have a scalar function times a vector function, or yeah, and it and I don't quite see how they do it, but anyway, I hate to take up so much class time doing it. Let's back up and try to reproduce what they did, okay? What I was starting to do, and I talked myself out of it, okay? It's right here. And they still are skipping a bunch of steps, and it make it seem like their technique is easier. I have a feeling it's not that much easier, maybe a little bit. I hate to do this because this is taking so much class time, but it's not a trivial thing here. Okay. So what I was going to do is 1 over the square root of 9 plus 16t squared times 3i plus 4tj. All right. Now they want to take the derivative of that, which is what we were trying to do. Okay. Now, this is a scalar function times a vector function. And this is the one that we're talking about way back there. What was that? 12. I think it was. Nope. Yeah, 12.2. Okay. This is number 3 is what I should have been saying. Derivative of a scalar function times a vector function. And it's just the product rule there again. Okay? So I think what I would do is write this as 9 plus 16t squared to the negative 1/2 power times 3i plus 4tj. Okay, whatever. I didn't need brackets there, but I'll take them out. Okay. Now, the t prime. First times derivative of the second plus second times derivative of the first, right? Okay, so which you want to do first? I don't really care much. We're doing this one, product rule. Okay, do that first, times the root of the second. Okay, so this will be 9 plus 16t squared to the minus 1/2 times 4j, right? Plus, only this will be a minus here, ultimately. Okay, derivative of the first, which is 16t, very good. 9 plus 16t squared to the negative 3/2, right? Derivative of the first, right? Skip so many steps you. Okay, we did this one times the root of that. That's it. Plus, root of this.
I see. I thought it was a positive 1/2, not a negative 1/2.
Yeah, it's a negative 1/2 here, right? And that's why the minus showed up here. And 1/2 of 32 was 16t, so that's where that came from. This thing to the minus 3/2 times 3i plus 4tj. Okay. Now, this is ugly, okay? But we should be able to do something with it, okay? And what they suggest we do with it is this. Least common denominators here are 9 plus 16t squared. Are we out of time? Okay. Yeah, 10 minutes over. What do you let me do? 2 minutes over, okay. All right. Can y'all finish this at home, or do you want to finish it in class? Huh? Want to finish it in class or home?
Class.
In class. Okay, we're down to this step right here. And we'll pick up there next time. Okay? Let me also give you a few homework exercises to do. We didn't get nearly as far here as I wanted to. Okay, homework exercises here. Any of the odds 3 through 7, they're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. 9's at Calc View. And you can start trying to do 15 through 19 if you want to, but we haven't finished one of those, so that's up to you. Those are all at Calc Chat, but 15's at Calc View. We'll pick up the rest of those next time. Okay, sorry about that. And today